Hello everyone, my name is Roy Jafari and I would like to welcome you to another video of data mining series. As I promised in one of the videos before, in this video we are going to specifically talk about the evaluation metrics and tools that we can use for binary classification. We have already seen a few tools and evaluation metrics that we use for general classification, but in this video we are going to see a few more methods for only binary classifications. And of course, the distinction between binary classification and general classification is that binary classification has only two possibilities, 0 or 1, pass or fail, success or unsuccess. So you might be surprised that there are a lot of cases that we need binary classification to help those decision-making environment. All right, let's look at this slide. Okay, so after a little bit of recap to talk about the general methods that we use for general classification, we're going to discuss many different things in this video. I'm hoping that the video is not going to be too long, but we're going to discuss the assumptions behind these generic classifications and generic metrics, and we're going to also see examples, and through those examples we're going to talk about precision, recall, sensitivity, specificity. So that's not actually written here, so let me just go ahead and add it here. So before precision and recall, we're going to talk about, and then also we're going to discuss the relationship between recall and precision. Of course, the same exists between sensitivity and specificity. And also we're going to talk about ROC curve, area under the curve, and eventually we'll discuss F-score. So let's get to that. We discussed and we saw that, when we evaluate a general classification model, we normally use one of these generic metrics. We use number of misclassifications or accuracy or error rate. And one thing that we have to pay attention is that these generic metrics have, some assumptions behind them. And those assumptions are mistake equivalence, which means that the consequences or the reflections of different types of mistakes on these evaluation metrics are the same. And also object sameness, meaning that all of the data objects in the analysis will have the same amount of weight on the results of these metrics. So in this video, we're actually going to only focus on the mistake equivalence, and by we're going to use this as a lead-in to our conversation for needing more specific metrics for binary classification. Alright, so let's discuss this example, this binary classification example. If we want to have a data analytics breast cancer diagnosis, we have to code or we have to design and solve this task as a binary classification task. And this binary classification task, of course, our data objects are patients, or categories are if the case of cancer is malignant or benign, and if our the attributes we are using to solve this classification problem, or like find a connection between the independent attributes and independent attributes, are the medical measures, right? So in this classification problems, we've got two types of mistakes, right? When we have any binary classification, we always have two types of mistakes. We have the mistake of false positive, meaning that we decided the case is cancerous by mistake. False positive, positive is cancer, false we did it by mistake. And we have a case of false negative. meaning that we decided that the case or the patient does not have cancer, and we did that by mistake, right? So these two mistakes, when we look into this case study and to this example, are very different from one another. While false positive is merely a false alarm, a request from the doctor or from your data analytics, automated data analytics, for you to perhaps use more accurate, perhaps more expensive testing, the false negative is far more consequential. It's us not being able to detect the cancer. And while a false alarm might just lead to an unnecessary testing, a false negative may lead to consequences such as patient's death. So you can see that the mistake equivalence assumption that are behind accuracy, error rate, and also the number of misclassification does not hold here, right? You're obviously seeing that false negatives are far more consequential than false positives. All right, so this is the contingency table that we can use to show how we derive accuracy and error rate based on these two types of mistakes and two types of correct classification, right? If we have we actually have positive and we predict positive, we have true positive. If we have negative and predict negative, we have true negative, and of course we have these two mistakes, right? So we use true positive plus true negative divided by the whole number of cases, right? So everything has to be in this table. So this is the total number of cases, right? This is the n. And this is how we sort of see accuracy. I mean, for us, the goodness of true positive and true negative are the same as the undesirability of false negative and false positive are the same when we are using accuracy and error rate. But we did see in this example that, in the case of breast cancer diagnosis, we did see that false negatives are far more consequential and more undesirable than the false positive. So if we want to see a metric that actually capture this, we have to find metrics that only uses these in its essence, right? We do see that false negative is used in the error rate, but also false positive is used. But we do know that false positive is not undesirable as false negative. False negative is far more undesirable. At the same time, while true positive is way more desirable, true negative, which is finding that the patient is not cancerous or does not have cancer, which for the most part are a lot of the patients out there, right? The rate of having breast cancer is not a lot, right? So because of that, true positive is also way more important and makes us more happy when we find a true positive. So let us discuss the possible metric that we can use is true positive divided by the whole number of positives. So this is all of this is all P and this is all N. Let me use another. These are all N, right? And specificity is true negative, which is this, divided by that. And sensitivity is true positive divided by the whole number of positive, right? So now we have a metric that can focus on what is more important for us in the case of breast cancer diagnosis, right? So if we were to choose one of these two metrics for our breast cancer diagnosis, which one would we choose? Of course, we choose sensitivity. But before continuing with this video, let me talk a little bit about what are sensitivity and specificity. Sensitivity is also known as true positive rate. It is how many relevant items have been selected, right? So that's what we are trying to capture with sensitivity. The relevant items here are the positives, right? So we are trying to check how many relevant items have been selected. So that is, and in another word, we can say this is the percentage of the sick people that we have successfully detected, right? So that's sensitivity. On the other hand, the specificity is the true negative rate. It is, sort of answer the question, how many negative selected elements are truly negative, right? So we are trying to answer this question. How many of these ones that we have selected as negatives are actually negatives? So most of the time, because in the cases of classification, we are more interested in finding the positive one, the more important attribute, possibility of the binary attribute we're trying to predict. So most of the time, we probably are more interested in using sensitivity than specificity. All right, so let's move on. And the next thing I want to talk about here is the fact that accuracy can be driven from sensitivity and specificity. These are all positive cases, right? You see, these are all positive cases. Then these are all negative cases, right? Then here we have true positive. Then here we have false positive, because this is the part that we have selected. And then here we have true negative, and here we have false positive. False negative, my bad. Here I have false negative. One thing that we will actually see in one of the slides in this video, one of the next slides, is that the fact that accuracy is driven from specificity and sensitivity, it could be a problematic things about accuracy that we will discuss. So now let's discuss recall and precision. Recall and precision are kind of similar to sensitivity and specificity, but they have some differences. The similarities start as you can see, recall is equal sensitivity. They are the same thing, right? So this is recall, so this is all of the positive cases, right, divided by the true positive, right? So this is exactly as sensitivity. But then precision, instead of focusing on total number of negatives, it focuses on the total number of selections, right? So this is what precision focuses on. It's true positive plus false positive. This is what precision focuses on, right? Precision says this is the most important things for me, right? I don't even want to consider the true negatives. I mean, they're so inconsequential. So that's what precision pays attention to. So if we pay attention here, if we look at this slide, This says recall, the same as sensitivity, is how many relevant items are selected. But precision says how many selected items are relevant. Pay attention to the wording. It's paying attention to, our selection here. On this one, it's paying attention to all of the positives. So that's, precision and specificity are not the same thing, but sensitivity and recall are the same thing. So there is an interesting relationship between recall and precision, and by trying to improve recall by changing the algorithm, modifying the algorithm, or doing other things to improve recall, we end up losing precision. And vice versa. If we focus on improving precision, we end up losing recall. We end up, so it comes at the cost of recall. There's the same type of relationship between sensitivity and specificity. Here we want to see an example of that and and see what we mean by that. So we go back to our case study. We want to do a binary classifications of breast cancer diagnosis. We want to basically classify if our patients are malignant or benign. I've used a famous breast cancer Wisconsin dataset, which has 699 data objects, and it has 9 independent attributes and not 1. So as a classification task, this is what we want to achieve here. We want to connect our independent attributes to our dependent attribute, right? So for what we are going to see in these slides, I have used an MLP, which is an artificial neural network. It's basically doing this, capturing this connection by its very specific, relevant, perhaps confusing at this point, design. Of course, in one of my future videos, you are going to be able to learn what MLP is and how MLP goes about doing what it does, which is finding this connection. But anyway, let's pay attention to the results here. So when the MLP is through, it gives us basically a probability value for each of data objects in the test set, right? And these are the probability values. It says the probability of benign case, and this is the probability of having a malignant case, right? And these are all just 12 data objects, 16 data objects. These are a sample from, right? So these are probability values. How do we go from probability values to a classification, right? There are very simple approaches here. One of the approaches is to say, let me just use 0.5 as a cutoff. If the probability is larger than 0.5, I just think or just decide that's going to be malignant, right? And that's 0.5 is when you want to perhaps maximize your accuracy. Think about that. But let's just use that cutoff point as 0.5. So our cutoff is 0.5. So if I use cutoff 0.5, these would be my decision. This would be benign, this would be malignant, benign. So that's just one way of doing it. But one person can be a little bit smarter than this and says, you know what, don't we want to sort of like see if there is any possibility of malignant? If we have malignant, right? How about I change the cutoff from 0.5 to 1.1 for malignant cases, right? If I do that, I change the chance of having a malignant because I know malignant cases are more costly. So I'm okay having more false positives so I can have less false negatives, correct? So that's why I'm doing this. So cutoff point 0.1. In that case, so I'm just paying attention to this probability value. I mean, of course, this probability is 1 minus this one, but I'm just going to pay attention to that one, right? So here, this would be benign, would be malignant, would be malignant, would be benign. This would be malignant, malignant, benign, malignant. Oh, this actually would have been malignant. Malignant, benign, 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 malignant, and benign. Right? You see, there was one case that if I had chosen cutoff point 0.5, I would have decided benign. But when I'm choosing cutoff point 0.1, I am sort of like choosing malignant. And basically that is for me to sort of tip the classification a little bit, so there are less number of false negatives at the cost of more false positive. So that's basically that relationship I'm trying to talk about here. So one thing we can do actually is computationally calculate what would be the performance of MLP, accuracy wise, recall wise, precision wise, sensitivity wise, specificity wise. If we were to change this cutoff, right? So if I change this cutoff, from a very small value, you see it's a very small value, all the way to a larger value that's possible, which is almost 1, right? If I change this cutoff, right, when it's very small, the smallest indication I see that there might be a malignant case, I decide it's malignant case, right? So that's why my sensitivity and recall are 100%, are the best possible, right? It is actually till 14% that it gives me that, when the threshold is 14%, it gives me that assurance that, your recall is going to be great. But you can see as my sensitivity start to decrease, because I am improving or increasing the threshold, my precision starts to improve. At some point they reverse, and you can see that now precision starts improving. And of course, do you remember what I said? If you want to achieve the highest possible accuracy, you want to go somewhere around here, like 0.5. Do you remember that? That's the highest possible accuracy, right? That's around that number. So that's the relationship. If you try to improve your precision, your recall is going to go down, and vice versa. So to capture this, this relationship in one plot, this is what we use. We use receiver operating characteristics. So basically, receiving operating characteristic plots sensitivity and specificity on one plot, so you can look at it and get some understanding of how well your classification model is working. So for you to be able to have an ROC, you have to experiment with all of the possible thresholds, and of course you have to have a probability value for each of your data objects, right? So if you have just a class label, you have an algorithm that just does classification with no probability, then you cannot do ROC. But if you have probability values and then you experiment with all of the thresholds, then you can come up with this ROC. And what's an ROC? ROC is basically this. You have a plot that on the y-axis you have sensitivity, and on the x-axis you have 1 minus specificity. Of course, this is also known as true positive rate. This is known as false positive rate. False positive rate. 1 minus specificity. Alright, so when you draw those points, so basically what you would do here, from the top here, you start putting specificity and sensitivity on your chart, right? So you start putting these values, and you start from very high sensitivity, right, and very high 1 minus specificity. So you start from here. So actually, if you want to do this, we have to go from here, right? So we move from here up, right? So we have 1 minus specificity, which is 0. So we start from here, and then that's from there. So we start, and it looks something like this. It will look something like this. So that's ROC curve, right? So here's another example. Here we have, true positive and false positive. Again, we have to come from all the way from below. So for example, this is this point, right? So this is that point. Let me see, let's for example find this point. No, that's not good. Let's for example find this point, right? So 1 minus 11 is like around 90, right? So it's around 90. So it's around here. It's that point. For example, let's find this point. For example, this one is, for example, this point. It's around that point, right? So this is what ROC curve is basically. So it gives you the opportunity to be able to evaluate the performance of your classification model by not having a threshold. So you don't have a threshold, right? You don't assume any threshold. Therefore, it allows you to just see how well what is the quality of this probability value that your model has given. So, how do we know which model is better? So, for example, if we want to compare model 1 and model 2, here on these ROC curve, model 1 is doing better. Basically, the more upward towards the left you have, that's a better model. So M1 is better. This represents a random predictor. So if you have anything below this line, it means your classification model is doing worse than random. Alright, so what is our area under the curve? As great as ROC curve is, it's a really nice visual tool. But for us to be able to use it, we have to actually engage human participation. Right? You have to see it and sort of look, let's see which one is doing better. To sort of combat that, one way to sort of have an estimate of which one is doing better is calculating the area under the curve, right? So calculating this area, seeing what is this area, and then comparing that with the area of the other curve or any other ROC, then it would allow you to be able to use AUC as just one summarizing number that can be used inside algorithms. So that's the whole AUC thing. AUC thing. Now pay attention, this is a really good approximation. If you have if one model has larger AUC, it does not guarantee that it is actually better than the other model. It's a really good approximation though. Alright, so let's come back to that issue we were talking about accuracy. This is not so great that accuracy is basically a combination of sensitivity and specificity. Let's talk about why is that. And that's the issue when we have imbalanced data sets, right? So this is a balanced data set. We have as many number of positive cases as we have negative cases. So if we have an unbalanced data, right? So let me get imbalanced data. So now we do our classification, right? And then we select these as our positive cases, right? By no stretch of the imagination, this is a good classification, because what's important for us is being able to find these positive cases, right? And out of the 5 that we've selected here, only one of them is successful, right? So our sensitivity here, all right, so our sensitivity is going to be 1 divided by 4, right? But our specificity is going to be 28 divided by 32, right? So the specificity is a much better performance, but sensitivity is very low. But pay attention here, right? That's the problematic part. Because of the way this is, sort of derived, this is the way this is set up, the importance or the weight of sensitivity is very low, right? If pay attention here, it's going to be 4 over 32 plus 4. But the importance of specificity is way higher. It's going to be 32 divided by 32 plus 4, right? So as far as what accuracy is concerned, if you were to use accuracy for this case, which you don't have as many positive cases, it's basically going to, for the most part, show how well you are finding the cases that are negative. You're just basically giving a much higher weight to specificity. So pay attention. For the most part, very often, the binary classification has to use an imbalanced data, right? Something like this. So you never want to use accuracy for imbalanced data because of this problem, right? So what do we do? One of the thing is you want to use more specific metrics such as specificity, sensitivity, or recall, or use F-score, right? F-score is the combination of precision and recall. It's basically harmonic mean, and it basically equally weight these two values, right? These two metrics. And the way it's set up, it's sort of not sensitive to the number of negatives in your data, right? So let's for example, let's see an example here, right? So that's when our class is not imbalanced, or our dataset is balanced. This is a balanced case. When we don't have a balanced case, so let me draw that again. Right, so this is our imbalanced case again, right? So let's say we do select something like we did from the previous slide. This is very comparable, right? Let me actually check. Yeah, so this is something like that. So now if we pay attention, our recall is going to be based on these 4 values, right? Recall is going to be 1/4, and our precision is going to be also 1/5, right? So now the recall and precision, this one only matters about the number of positive. This one only matters about the number of selections. So even though precision and sensitivity, as we saw, remember, behave very similarly, right? Precision and specificity, right? They behave very similarly. But at the same time, precision has one advantage, and that advantage is that it does not take into account the large number of negative cases that it is very common in our classification tasks. So every time you have an imbalanced class data set, you want to use F-score if you're looking for a more general metric, meaning that false negative and false positive are the same for you, or you want to look at something that these two are similar. And if you have knowledge of false negative being more important or false positive being more important, you want to either use precision or recall, or sensitivity or specificity. But you never want to use accuracy as a metric for an imbalanced data set. Alright, so let me offer you some summary. In this video we talked about the assumptions behind general classification metrics, and then we use that as a lead-in to talk about sensitivity, specificity, precision, recall, ROC curve, area under the curve, and F-score eventually. So now, after having watched this video, you're equipped with a really good knowledge of being able to successfully evaluate binary classifications. Until the next video.